Hello, everyone, and welcome to a presentation on in-memory databases by Group 7. Today, we're going to cover a kind of database that hosts its primary dataset in volatile memory or random access memory and minimizes all interaction with secondary storage, that is to say, hard drives and solid state drives. To provide an overview of the topics we're going to cover today, we're going to start with why in-memory databases are relevant today, some performance characteristics of these kinds of products, and some of the concurrency mechanisms that are unique to in-memory databases. There are also some recovery aspects of in-memory databases that differ from their disk-based cousins, and we're going to cover that as well later in the presentation. And to end, we're going to discuss some test results from an experiment we ran to validate the research that we were finding. To begin with relevance, it was inconceivable in the 1980s to store an entire data set in random access memory because the random access memory capacity of the time simply wasn't sufficient to support the data sets that they wanted to manage in these database management systems. So they started to emerge in the early 1990s, and in the modern day, they're used in industries that rely on low latency database operations. Oftentimes, they support web applications and track user session information so that they can run quick queries on that data in support of that web application. They utilize a unique architecture that minimizes I/O operations. Remember, we are trying not to rely on secondary storage as much as possible. And it also tends to use pointer-based data representations because in-memory databases steer away from traditional page-based implementation of data representations, and instead implementing key-based data stores or pointers that reference the data more directly.
Hello, everyone. Before we start talking about in-memory database performance, let's talk about in-memory databases versus disk-based databases. First, in-memory databases are databases where you store and update changes of the data in the memory. So you can see from the graph using the main data. While disk-based databases instead have the data in disk, and you move that data from disk into RAM to do the operations. So now, first, we're going to talk about the disadvantages of in-memory database performance. So not all in-memory databases are good for different types of workloads. A big classic example is a study of doing mixed workloads for in-memory databases for the right performance, such as when you have OLTP and OLAP for the type of load that you have to do, as the OLAP would slow it down for different types of queries that we need to use. The advantages of in-memory databases, however, are that the I/O cost is lower because you don't have to move from disk to memory. Instead, you just do the operation on memory. So you can tell from the graph that this is the case. Concurrency, another two advantages is that the memory databases do not have to do long escalation strategies. This means that they have a lot less response time. And in-memory databases do have a little bit of extra overhead, but comparatively speaking, you only have just a bit more than disk-based. And then for parallel computing, memory databases are actually better when you have less processors, less CPUs used, because you can significantly improve the time as one is used and it's not distributed, while disk-based suffer very severely, comparatively speaking.
Hi, this is Alan. I will introduce the concurrency and control part. For the main memory database, multi-version concurrency and control is the most popular transaction management schema in use. The fundamental concept of the multi-version concurrency control is that the database management system will maintain multiple physical versions of the data record with different timestamps on them, allowing parallel transactions. This is a template for the record. The TXN ID, which is the write log, it indicates whether the record is under updating or writing. It will be set to 0 at the beginning. The begin TS and the NTS indicates the beginning time and the end time of the tempo versions. Pointer stores the address of any existing previous or next version of the record. We will introduce 3 main control protocols for the concurrency control. The first one is timestamp ordering. It uses unique transaction identifiers to pre-compute the serialization order of the transactions. For the read transaction, the timestamp between the begin TS and the NTMs will be executed, otherwise it will be abort. And for write transaction, it is only allowed when tempo is not locked. Therefore, for read transaction, it can read the previous version of the tempo, and the write transaction can execute it at the same time. The next one is automatic concurrency control. In this protocol, it assumes that conflict appears very rarely, and tempos are not locked when it is updated or read. However, there are 3 phrases: read, validation, and write. All the read transactions are done within the read phrase, and for write transactions, the content to be write will be stored on untempered storage and enter the validation phrase. In the validation phrase, the consistency of the database will be valid. If there is any conflict, then the content will be discarded, or it will be written into the database. The last one is two-phrase logging. In this protocol, the TXN ID and another read CNT, which is read count, will be used as the write and read log. The read transaction only can be executed when its timestamp is between the begin TS and the NTMs of the record. Otherwise, it cannot access the version of the tempo. And for the write transaction, it is only allowed to change the tempo when the 2 logs are both 0, which means the tempo is not logged for reading or writing. After the write transaction, the begin TS of the record will be reset to the transaction's timestamp, and the NTS will be set to infinite to indicate the lifetime of this version.
Okay, so crash recovery. There are 3 types of failures related to crashes that all databases experience, and that would be transaction failures, which is just an aborted transaction, system failures, which is when a database is connected to a power source and that power source is disconnected somehow, causing all the data that's sitting in RAM to be lost, and media failures, which is when HDD or SSD fail. So in-memory databases really excel at handling transaction failures, and that's because the data is primarily stored in RAM. And so that means that any aborted transactions operations are very easy to quickly discard compared to a relational database where in common implementations, those aborted actions have already been persisted to secondary storage. And so you have to roll back those operations, which takes additional IO and really slows things down. And this is kind of related to the goal that in-memory database designers have, and that's to avoid as much contact with secondary storage as possible. So system failures and media failures are something that in-memory databases don't really excel at recovering from, and that's why those are really what cause database crashes in this context. And so when a crash happens, 2 things are really used for recovery, and those are snapshots and logging. So snapshots are basically during periodic checkpoints where the data in main memory is copied over to a small section, an archive in secondary storage. And so these requests to move the data are asynchronous, so non-blocking, so there's at least that benefit. But the other option is that's also used as logging, which is when a transaction's operations are written before even the operations are applied. This is write-ahead logging, meaning that the operations are already recorded as logs and persisted into secondary storage. The logic of the transactions, though, it's not the data operations. And so that means that when a failure does happen, the operations have to be reapplied. When you're just reading from the logs, you have to read the transaction logic and reapply it on the data. And so this is why logs are much better for IO, because they're very cheap and you can keep them together and you can just flush them whenever it's best. But snapshots are much better for faster recovery. And because all you have to do is take that archive in secondary storage and just overwrite main memory. So both are used, but more snapshots is definitely nice for a quick recovery. But as you can see in implementation, Normally, a slow recovery is what is used, and that's because of our current architecture. We can afford to have slow recovery because a lot of times these in-memory databases are in multi-node architectures where you can spin up multiple instances like a Redis cluster. And so that means that if these databases are dealing with, a database is dealing with multiple transactions and then fails and has a slow recovery, another instance can come in its place and start handling those transactions. And so that means transaction speed is still very good. And yeah, sure, recovery is taking a while, but it doesn't matter because there's more instances. And so that's what makes these systems the ideal candidate for OLTP systems.
Performance testing. We believe we are working with a technology that has incredible potential for improving querying latency. We decided on 4 situations to test this technology. First, an in-memory cache with a hard disk main storage. Second, a database in a hard disk drive. Third, a database in a solid state drive. And our aim with this was to test the 2 types of main storage. We wanted to see if there was a latency and speed improvement between them. And then finally, for 4, database purely in memory. Our goal here is to get an idea of how powerful this technology is compared to more common and traditional systems. We decided to use MySQL for the traditional systems and Redis for the new blazing fast implementation. Implementing the tests. I feel it important to mention how we test these implementations. So we decided to build and test with Redis backed by MySQL in a Docker container using PHP. Trying to avoid needless complication, we decided that a simple PHP page that could check to see if the key was in a Redis database would be an adequate test. If it wasn't, we retrieved it from MySQL and then stored it in Redis. We did this 10,000 times with the same query within a Python class file. We actually used a Python class file for every test, but that's not really important. As I said, we wanted to test the performance between the different types of storage. We felt it inadequate to solely test HDD, as it is an older technology, and SSDs are much more reliable and cost-effective today. So for this, we simply moved the MySQL data folder between one disk drive to the other disk drive on my local machine. One problem we had with Redis was inputting a CSV file. It didn't like it. So instead, we created a script to insert a key value pair of II, where I is every number between 1 and 10,000. And then created another Python class to retrieve every key value pair and calculate the time. The results. So this was our base run, the simplest implementation and our perceived worst scenario. As you can see, it took on average 55 seconds to complete 10,000 queries. This was a bit of a shock, as we thought that the SSD would be faster, much faster. I think that this test was the most eye-opening, though, as it shows it doesn't matter how fast the drive is if the latency is still rather high. This was impressive. I ran this test more than 3 times and pored over the code repeatedly before trusting it. It took Redis 0.8 seconds to retrieve every number between 1 and 10,000. This test was a bit more difficult to comprehend. The major difference with this test is that in each of the 10,000 queries, it had to create a new Redis connection and run a whole page. So calculating the actual time for the query proved a little difficult. So if you like, though, you can clone the repository and deploy the Docker container yourself and see the speed difference on the web page as it's actually printed there. And yeah, that's performance testing. Thank you very much.
To conclude our presentation, let's cover some takeaways. In-memory databases are database management systems that store the active data set exclusively in volatile memory. They minimize interactions with secondary storage like hard drives and solid-state drives. Additionally, from a performance perspective, they tend to excel under OLTP workloads. They can handle small transactions very efficiently, but they falter in answering OLAP queries, which tend to be larger, more analytical queries that require some kind of secondary storage persistence to handle in large volumes. From a concurrency perspective, in-memory databases tend to excel in single processor parallelism, where disk-based architectures tend to require multi-processor environments to effectively implement parallelism. And in-memory databases also allow for novel granular blocking strategies, which empowers them to handle higher volumes of concurrent user sessions. Lastly, from a recovery standpoint, in-memory databases are brittle to system failures because in the event of power failure, for example, RAM data is going to be completely erased from the system. There's no way to persist it until you can restart. As a result, though recovering from those kinds of failures takes a long time. They are, however, very resilient to transaction failures, and they support multi-instancing to compensate for the risk of a system going down. Thanks again to everyone who's watching today, and I hope that this presentation has enlightened you all as to what an in-memory database is and some of the characteristics you will normally find in these kinds of database management systems.